Hello, everybody. I am Haddad, Assistant Professor at Aix-Marseille University, and I'm going to present to you today the work entitled Comparative Design Analysis of Ultra-Low Power RF Self-Oscillating Mixer. This work has been made during the PhD of Sophia Fenni with my colleagues Slimane, Touhami, and Rahajandraibe at the conception design of circuit and system at IM2MP Lab in Marseille, in France. The main activities of the team are design of circuit and system for wireless communications and more recently for healthcare. This is the outline of my presentation. We can begin with an introduction of the work. Then I will present a context of the connected object and IoT, Internet of Things. Then I will present how to design self-oscillator mixer, what is self-oscillator mixer, and give some results before concluding. So in recent years, the wireless communication market has explosively grown with the multiplication of applications in smartphones, Internet of Things, nanosatellite, etc. And objects are becoming intelligent and smart due to the development of the communication technologies. And all types of these electronic devices are linked to each other, all sharing the data via the internet. So the scope of IoT is quite broad versus communicating devices and machine to machine. And we can see in this graph the explosion of the number and the constant increase of the number of connected objects. We are expecting to have about 30 billion in 2030. And this is used in different fields of applications, such as consumer, industrial, domestic, and also healthcare. So why we speak about healthcare? The connected objects are used in different applications, and people have all some kinds of equipment to measure the physiological data, such as ECG, temperature, and all of this stuff. But people start to be aware of the existence of connected objects for health. For example, in France, 11% of people own connected measuring devices, and this number is on the rise. And the connected objects now are perhaps at the center of a new health ecosystem. For example, the case of the chronic medical condition, solution can be used at various stages. First in prevention, then also to build a more appropriate lifestyle once the patient is actually suffering from illness, and also to monitor vital parameter after hospitalization. Here an example of existing platform, which is called Patient Intelligent Monitoring Center. So to facilitate the improved communication between the patient and the caregiver, an improved medication compliance, also the control over unnecessary health care costs. This is the main objectives. And whereas monitoring of patients perhaps will be the key to the future e-health or healthcare. And this is the consequence of that is massive deployment of embedded technologies. So we need to monitor and transmit a huge amount of data, and this will require the implementation of power and cost efficient devices. So here we speak about the problematic of power consumption and cost. When we speak about IoT or Internet of Things, the topology of the network comprises nodes that will collect and transmit this data to a central controller. A sensor node has inside it an MCU, a sensor, a transceiver, a power block, and sometimes the energy management block. And in this work, we'll focus on the wireless transceiver part, the RF or radio frequency transceiver, since it's the part that consumes the huge or the biggest amount of power. When we choose to design an IoT device, we should choose first which standard of communication, of wireless communication we'll use. So for IoT, we can find two families, the sub-gigahertz and the 2.4 gigahertz bands. So sub-gigahertz, such as LoRa and Sigfox, dedicated to low data rate applications, and 2.4 gigahertz, such as Bluetooth, BLE, Wi-Fi, WiMAX, Zigbee, which is suitable for high data rate. So it's necessary to have a good choice to serve the transceiver designer needs. And the main design challenges of the transceiver are low power consumption, high integration, high resolution and sensitivity, and also low cost. And when we speak about transceiver and reducing the consumption or the power consumption of the transceiver, we have two possibilities. So either ultra low voltage operation or current reuse, which are the most used techniques. So here we can see the voltage headroom, which is given by the supply voltage. So we can reduce this voltage to reduce the power. And it can be possible with either using the inductive loads and transformers, but this will increase the chip area, or by using the sub-threshold region, but this we know that transistors will be sensible to PVT variation, process, voltage, and temperature variations. In the second case, we use the current reuse technique. So here, habitually, blocks are made in cascade, but in current reuse, blocks are stacked. And here we can share the DC current and we can save the current. So we reduce the power consumption. An example here in the figure is an example of front end of transceiver used in wireless communication. We can see the antenna, the LNA, then they have the mixer to go to the intermediate frequency, IF, and the VCO, the oscillator, before going to the filter and the digital part of the front-end transceiver. The possibility here, or this work, focus on stacking together the mixer and the VCO, because they are generally designed as separate blocks, but here we will merge both building blocks in one circuit, and the resultant circuit is called self-oscillating mixer. Abbreviation is SOM. So ultra low power consumption could be achieved because of the DC current reuse between the mixer and the oscillator. And in this SOM design, the first constraint is to choose the appropriate topology. Which topology to our circuit, and which topology of each block, the VCO and the mixer. So concerning the oscillator, usually LC VCO, inductor capacitor VCO, is recommended since it consumes less power than ring VCO for a given phase noise requirement. And concerning the mixer, Gilbert active cells are usually used in these SOM circuits also. So now we choose the topology of our building blocks, and then how to merge them together. Most SOM topologies in literature are based on two configurations. Here we can see the first configuration, in which the oscillator is stacked above the mixer, which is led by an RF transconductor stage. Here we can see that the RF input signal is applied into the transconductor stage of the Gilbert mixer, And then the resultant signal is multiplied with the LO signal applied to the switching core. Then the obtained IF current here is converted through the load to the switching core. In the second configuration, the oscillator now is below the mixer. The LO and RF inputs are injected into the switching pair. In this case, the more appropriate mixing topology, the commuting mixer, in which one stage of transistor can be used simultaneously as a switch and as a transconductor. So the two-sum circuit here have been implemented on 130 nanometer CMOS technology, operating at 2.4 gigahertz. For the first configuration, we can see the schematic in this graph. So the LC-VCO is stacked above the double balanced mixer. The LC tank defines the oscillation frequency. Then the NMOS cross-coupled pair constituted by transistor M5 and M6 are used for tank loss compensation in the oscillator. Then capacitor C0 gives the path for LO signal, which drives transistor M1 to M4 via capacitor C1 and C2 to achieve the current switching function. M1 and M4 constitute the switching core of the mixer. What is the operating principle of this first configuration of sum? In the first half LO period, M1, M4, and M5 are on, they are open. The output RF current of M0 flows into them through the RL and C0, while M2, M3, and M6 are off, resulting to an AF current IF plus. We have no current in IF minus. In the second half of the period, it changed. So M2, M3, and M6 are on. The current flows through them like this, achieving a complementary operation with a resulting IF current. And the differential current here is converted through the load resistor into an output IF voltage. The cross-coupled pair of the VCO M5 M6 contributes to the switching function without perturbing the natural operation of the mixer, while M0 here acts as a transconductance GM. In the second configuration, the mixer is stacked above the LC-VCO, so it appears as an external load of the VCO. Here, the LC tank defines the oscillation as all structure of VCO. The LC-VCO uses a PMOS cross-coupled pair constituted by transistor M5 and M6 for tank loss compensation, instead of NMOS pairs usually used in literature. The RF signal is applied to the gates of transconductors M1 to M4 that are switched on off by the LO signal fed into their sources. The output LO signal are chosen to be the sources of the PMOS cross-coupled pair here instead of their drains to avoid and to isolate the resonator from any load effect. So the loading problem can be avoided with this structure, which improves the quality factor and then the phase noise performances. For the operating principle here, we can see that M1 to M6 transistors must operate in saturation region. The transconductances of these transistors depends on the LO signal injected to their sources. Transistors M1 to M4 are switched on-off according to the VLO variation here. We can see in this graph the VLO signal. If we consider VLO DC as the DC voltage, VLO off is the minimum value of VLO tuning, turning off this transistor M1, M4. So when VLO is less than VLO DC, transistors are on, providing a certain amount of value of GM. So we can see it here because of the figure. While VLO increases, GM decreases until it's off. We don't have GM for VLO greater than VLO off. Concerning the simulation results, we can speak about the conversion gain, the phase noise as essential performances, the power consumption, and linearity. So we begin by the voltage conversion gain that can be expressed as GM multiplied by R divided by 2. For the configuration 1, GM is equal to GM of transistor M0, and R is Rx parallel with RL. RL is the load, and Rx are resistance seen at sources of the cross-coupled pair. And in configuration 2, it's GM is equal to GM of switching pair, switching transistor 1 to 4, and R it's only the load resistor. So the design challenge here is to judiciously size the transconductance GM in the mixer, since the conversion gain depends directly on the GM value. We can see in the figure on the left the response, the obtained result of the conversion gain for both configurations. The configuration 1 has a better and a higher conversion gain, so almost about 18 dB, while it's only 9 dB for configuration 2. And when varying the voltage supply by plus minus 10%, we can see that the behavior is almost stable for both configurations around these values. To verify the stability also of the performance, the conversion gain of the both configuration, we made additional Monte Carlo simulations with 600 runs, including random variation of process and device mismatch. So we work at 2.4 gigahertz for an IF frequency of 10 megahertz. Both configuration here we can see have very narrow spread, showing a gain stability versus process and mismatch uncertainties. We can see a standard deviation of 0.003 and 0.002 with sigma of 0.007 and 0.054 for configuration 2. So we can say that both some circuits are very stable against these variations. The second performance is the phase noise of the sum circuit. So we can see in this figure that the phase noise of configuration 1 is better than configuration 2 because the transconductance GM0 that addresses a part of the low noise amplification too, so it reduces the noise. We can have we have minus 113 dBc by hertz for the configuration 1, while we have minus 110 dBc by hertz at 1 megahertz offset frequency from the carrier. And when varying the VDD, the supply voltage, we can see here also an almost stable behavior of the phase noise, maintaining the stability of this kind of merged self-oscillator mixer. In this table, we made a summary of the performances in terms of power consumption, RF frequency, phase noise, and conversion gain for both configurations. and this is made for different process corners called TT for typical, FF for fast fast, and SS for slow slow. It's for transistors, PMOS and NMOS. We can see that the maximal oscillation frequency along with the lowest power consumption are attained from SS corner in both sub configurations. Second point is that the maximum variation of the power consumption and the conversion gain are given for FF corner. So it can be concluded that the FF corner is favorable for high gain and phase noise, but it's adverse for power consumption. In this table, there is a comparison of the obtained performances with both configurations with other some works in the state of the art. We can see that we have the smallest here, an ultra low power consumption of sub milliwatt, 0.6 and 0.8 for type 2 and type 1 configurations. A small area, surface area is 0.24 millimeter squared. And concerning the linearity, the main source of distortion in type 2 that we can see here in the IIP3 is comes from transistors M1, M4. They have non-linearities. The larger are these transistors, the higher is their non-linearity. So it can explain this difference. So to conclude, in RF transceivers, design of low power circuit is very challenging to judiciously choose the sizing of the components. Here, two configurations of monolithic self-oscillator mixer have been designed in CMOS technology. It has been noticed that stacking the mixer and the VCU on the top of each other in this SOM circuit induce a power consumption and cost saving. An ultra low power around 600 microwatt and 800 microwatt have been carried out through 1.2 volt supply voltage in both configurations. These obtained results confirm that the proposed SOM circuit have a high robustness against voltage and process variations, which makes them a good candidate to design ultra low power system for IoT applications. And thank you for your attention.